The subject of black holes has always fascinated many people because they're objects that have remained mysterious. However, it's a great time to be alive as scientists have found the closest black hole to Earth, which you can even see with your own eyes. What is the name of the black hole and how close is it to the Earth? In this video, we dive into the closest black hole to Earth that can be seen by the naked eye. Don't be fooled by the name. A black hole is anything but empty space. Rather, it's a large amount of matter packed into a very small area. Imagine a star 10 times the mass of the Sun squeezed into a sphere the size of New York City. As a result, nothing, not even light, can escape the gravitational field. For centuries, people have imagined a massive, dense object in space from which no light could escape. Black holes were most famously predicted by Einstein's theory of general relativity, which demonstrated that when a massive star dies, it leaves behind a small, dense remnant core. The force of gravity overwhelms all other forces and creates a black hole if the core's mass exceeds about 3 times the mass of the Sun, according to the equations. The majority of black holes form from the remains of a massive star that explodes in a supernova explosion. Smaller stars collapse into dense neutron stars which lack the mass to trap light. But if the total mass of the star is large enough, we're talking about 3 times the mass of the Sun here, no force can prevent the star from collapsing under the influence of gravity. Now, a strange thing happens as the star collapses. As the star's surface approaches an imaginary surface known as the event horizon, time on the star slows in comparison to time kept by observers far away. And when the surface of the star reaches the event horizon, time stops and the star can no longer collapse. It becomes a frozen, collapsing object. Stellar collisions can produce even larger black holes. Swift NASA Space Telescope observed powerful fleeting flashes of light known as gamma-ray bursts shortly after its launch in December 2004. After collecting data from the event's afterglow, Chandra and NASA's Hubble Space Telescope came to the conclusion that powerful explosions can occur when a black hole and a neutron star collide, producing another black hole. Although the basic process of formation is understood, one persistent mystery in black hole science is that they appear to exist on 2 radically different size scales. On one end, there are countless black holes, the remains of massive stars. These stellar mass black holes, which can be found all over the universe, are generally 10 to 24 times as massive as the Sun. When matter is drawn toward a black hole, it can ricochet off the event horizon and be thrown outward instead of being dragged into the maw. Bright jets of material at near relativistic speeds are produced. Although the black hole cannot be seen, these powerful jets can be seen from a long distance. The EHT's image of a black hole in M87 required 2 years of research even after the images were taken, because the collaboration of telescopes, which spans many observatories around the world, generates an astounding amount of data that's too large to transfer over the internet. Researchers hope to image other black holes in the future and create a database of what the objects look like. The next target will most likely be Sagittarius A star, the black hole at the heart of our very own Milky Way galaxy. According to a study, Sagittarius A star is intriguing because it's quieter than expected, which could be due to magnetic fields suffocating its activity. Another study discovered a cool gas halo surrounding Sagittarius A star, providing unprecedented insight into the environment surrounding a black hole. So, how many black holes exist? According to a recent study, there could be millions of small black holes in our cosmic neighborhood that have yet to be discovered. This means that black holes could contain about 1% of all matter in the universe. To create a black hole, you must first create stars, because black holes are formed by the deaths of stars. So the researchers behind the study had to take a few steps back to figure out how many black holes there are in the universe. The first step is to simulate the evolution of galaxies over billions of years of cosmic history. After all, galaxies are the homes of stars, and their overall evolution influences how many of each type of star appear within them. Some galaxies, for example, can produce new stars year after year. Others may experience merger events that cause a burst of extremely high star formation, only to burn out and produce nothing of note again. The astronomers examined known observations of galaxy statistics over cosmic time, noting a general trend in galactic merger rates and demographics. Another important factor is a galaxy's metallicity, which is a measure of the amount of elements other than hydrogen and helium contained within it. Larger galaxies will have more gas, allowing them to form more stars. More metals, on the other hand, can improve gas cooling, allowing galaxies to produce new stars more efficiently. Using these building blocks, the astronomers created a model of the stellar population within galaxies, revealing how many small, medium, and large stars exist in the universe. Then they had to follow the evolution and, most importantly, the deaths of those stars. They used simulations to connect the properties of a specific star, that is, its mass and metallicity, to its lifetime and eventual demise. Only a small percentage of the very largest stars produce black holes, and simulations tell astronomers what percentage of a galaxy's stars go dark each year. The astronomers then had to monitor the evolution of binary systems because black holes can feed off of sibling stars and become engorged on their gas in the process. As a result, a black hole formed in a binary system will be larger than a black hole formed alone. The black holes continue to feed on any surrounding gas as they age, which astronomers also estimated. Finally, black holes occasionally collide in the darkness of interstellar space and merge. The astronomers had to estimate the rate of black hole mergers within each galaxy in order to produce an accurate survey. Astronomers were able to track the population of black holes over billions of years by putting all of the pieces together. They created a mass function, which is a kind of astronomical census that reports how many of each size of black hole exist at any given time. Unsurprisingly, the largest black holes, known as supermassive black holes, are far rarer than their smaller cousins. The researchers discovered that our universe contains roughly 50 million solar masses worth of black holes in every cubic megaparsec of space. A megaparsec is 1 million parsecs or 3.26 million light-years. If each black hole has a few times the mass of the Sun, there would be approximately 10 million individual black holes in the same volume. To put this in context, the total mass contained by black holes is approximately 10% of the mass contained by stars. So for every star visible in the night sky, there are many black holes lurking between them. In contrast, supermassive black holes are extremely rare, with each galaxy typically hosting only one of these monstrosities. Overall, black holes account for about 1% of all baryonic matter, as opposed to dark matter in the universe today. The vast majority of baryonic matter is found in loose nebulae. Now, black holes are impossible to see because they swallow light, so how do scientists study them? Black holes were purely theoretical for a long time, or at the very least, collapsed stars were, as they had yet to be given their more intriguing name. The term black hole is frequently attributed to American physicist John Wheeler, but its origins are shrouded in mystery. The term was first used at a meeting of the American Association for the Advancement of Science in January 1964. It's unclear who coined the phrase, but Wheeler quickly adopted it and popularized it. Now, it may appear that looking for black holes is a waste of time. How can you see something that does not emit light? However, as the physics of black holes evolved, scientists discovered that there were alternative routes available. Because astronomers cannot see the hole itself, they must look for its effects. When matter is dragged into a spinning hole, which pretty much everything in the universe does, it should produce an accretion disk which glows brightly as a result of friction, as well as distinct jets from the poles. Then there's the gravitational pull. The black hole may have an effect on nearby bodies. This is an ancient technique that was once used to infer Neptune's existence. Astronomers investigated how Neptune's gravitational pull affected the orbits of the other planets. Hawking radiation is also present. Stephen Hawking astounded himself and everyone else when he realized in 1974 that black holes couldn't be truly black. His understanding of quantum physics, the science that governs very small things, and in particular, the uncertainty principle, sparked the idea. This means that localized energy can fluctuate dramatically over short periods of time, allowing pairs of quantum particles to emerge and then vanish before being observed. If this occurs near a black hole's event horizon, one of these virtual particles may be drawn in while the other escapes. Hawking radiation is made up of these stray particles. This is unlikely to be visible from a long distance. Black holes appeared to be the natural endpoint for stars with masses at least 3 times that of the Sun. However, this scale is not a limitation of the black hole itself, but rather of its formation mechanism. In theory, black holes could exist on any scale, from microscopic to millions of times the mass of the Sun. there are roughly 4 categories, 2 of which have most likely been identified. Micro black holes and quantum black holes are at the very small, completely hypothetical end of the scale. For example, if the Earth collapsed, forming an event horizon about 9 millimeters across, a micro black hole would form, though there is no known mechanism for this to happen. Quantum black holes are even smaller, with sizes ranging from 5,000 protons and up. In theory, they could be created in a particle accelerator and would decay almost immediately. Current accelerators lack the energy to produce one without assistance, but if the universe has extra dimensions, this could lower the energy threshold to something reachable. X-ray binaries are the best evidence we have for conventional black holes formed by the collapse of a dying star. Material is accelerated from one normal star to an invisible star in these objects emitting X-rays. This can happen with a neutron star, but if the eating star has a mass greater than 3 times that of the Sun, it should be a black hole. Cygnus X1 was the first X-ray binary discovered to contain a black hole. In 1964, a powerful X-ray source was discovered, which was later identified as a black hole candidate in 1971. The X-ray source, which appeared to have a mass of 9 to 15 times that of the Sun, was removing material from a blue supergiant star in the binary. Kip Thorne and Stephen Hawking had a bet in 1975 that this was in fact a black hole. Hawking paid up in 1990 when better observational data became available. Meanwhile, a newly discovered black hole may be the closest black hole to Earth, and the best part is that you can see it in the night sky without using a telescope. The black hole, which is 1,000 light-years from Earth in the southern constellation, interestingly named Telescopium, is part of a system that includes 2 companion stars that are visible with the naked eye. Astronomers discovered this black hole while looking into what they thought was a binary star system, or 2 stars orbiting a common center of mass. They were observing the binary known as HR 6819 with the MPG ESO 2.2-meter telescope at Chile's La Silla Observatory as part of a larger study on double star systems. When the researchers analyzed their data, they discovered a third object lurking in the system, a black hole. Scientists were able to tease out its presence thanks to its gravitational interactions with the other 2 objects in the system. They were able to map out the star's orbits and determine that another massive, unseen object must be acting in this system by observing the system for several months. The observations also revealed that one of the 2 stars orbits the invisible object every 40 days, while the other star remains at a much greater distance from the black hole. They determined that the object is a stellar mass black hole, a black hole formed by the collapse of a dying star with a mass 4 times that of the Sun. The team confirmed that the system contains the nearest known black hole to Earth. The black hole in HR 6819 is one of the first stellar mass black holes discovered in our galaxy that does not emit bright X-rays while violently interacting with its companion stars, and the discovery could help researchers find other similarly quiet black holes in the Milky Way. There must be hundreds of millions of black holes out there, but we only know about a few. But because scientists now know what to look for, they should be able to find them more easily. Skywatchers in the southern hemisphere can spot the stars in the HR 6819 system without binoculars or a telescope in the night sky. The pair appears as a single 5th magnitude star in the modern constellation Telescopium near the border with the Peacock constellation at Parvo. The faintest objects visible to the human eye are at a magnitude 6.5 on the magnitude scale, where smaller numbers denote brighter objects. HR 6819 is currently shining at magnitude 5.4, just slightly brighter than Uranus, the dimmest visible planet, and is barely visible to our eyes. Of course, there are other black holes lurking even closer that have yet to be discovered. Astronomers estimate that our galaxy alone contains millions of black holes. The nearest known black hole after HR 6819 is in the constellation Monoceros. Astronomers spotted the black hole masquerading as a strangely tiny object dubbed the Unicorn that lurks just 1,500 light-years away. The nickname has 2 meanings. The black hole candidate not only lives in the constellation Monoceros, or the Unicorn, but its incredibly low mass, about 3 times that of the Sun, makes it nearly unique. Because the system is so unique and so strange, you know it definitely warranted the nickname of the Unicorn. Discovery Team leader Tharandu Jayasinghe, an astronomy PhD student at The Ohio State University, said in a new video explaining the discovery. The Unicorn has a companion in the form of a bloated red giant star nearing the end of its life. In about 5 billion years, our Sun will also swell into a red giant. Several instruments, including the All-Sky Automated Survey and NASA's Transiting Exoplanet Survey satellite, have observed that companion over the years. The researchers examined the massive dataset and discovered something intriguing. The red giant's light shifts in intensity on a regular basis, implying that another object is tugging on the star and changing its shape. Based on the star's velocity and the light distortion, the team determined that the object causing the tugging was most likely a black hole, one with only 3 solar masses. For reference, the supermassive black hole at the center of our galaxy weighs approximately 4.3 million solar masses. The black hole distorts the star into a football-like shape with one axis longer than the other, just as the moon's gravity distorts the Earth's oceans, causing the seas to bulge toward and away from the moon, causing high tides. So the most straightforward explanation is that it's a black hole, and in this case, the most straightforward explanation is the most likely. Because they're extremely difficult to find, such super lightweight black holes are extremely rare. Because black holes are famous for devouring everything, including light, astronomers have traditionally detected them by observing the effects they have on their surroundings, though we did recently get our first direct image of a black hole thanks to the Event Horizon Telescope, and the smaller the black hole, the less of an impact there is to see. However, efforts to discover extremely low-mass black holes have increased significantly in recent years, so we may soon learn a lot more about these mysterious objects. The field of astronomy is moving in this direction to really map out how many low-mass, intermediate-mass, and high-mass black holes there are, because every time you find one, it gives you a clue about which stars collapse, which explode, and which are in between. Another black hole close to the Earth is Gaia BH1. The black hole is about 1,600 light-years away in the direction of our constellation Ophiuchus, the Serpent Bearer. Initially, data from the European Space Agency's Gaia spacecraft led researchers to believe that this stellar system, the black hole's companion star, contained a black hole. But Noir Labs' Gemini North has now confirmed this. The black hole's companion is a sun-like star that orbits the black hole at roughly the same distance as the Earth orbits the Sun. But what does this black hole look like? Well, take the solar system and substitute a black hole for the Sun and the Sun for the Earth, and you get this system. While many claimed detections of systems like this had been made, almost all of these claims have since been debunked. This was the first unambiguous detection of a sun-like star in our galaxy's wide orbit around a stellar mass black hole. Gaia previously detected minute irregularities in the star's motion caused by the black hole's gravity. With this in mind, Gemini North measured the companion star's velocity as it orbited the black hole. It provided a precise measurement of its orbital period by doing so. Scientists only had 1 week before the two objects were at their closest separation in their orbits when they received the first indications that the system contained a black hole. Measurements at this point were critical for estimating mass accurately in a binary system. The ability of Gemini to provide observations in a short period of time was critical to the project's success. They would have had to wait another year if they had missed that narrow window. Gaia BH1 is roughly 10 times the mass of our Sun, making it a stellar mass black hole. Other black holes, such as those found in galaxies including our own, can be much more massive. This newly discovered black hole has also gone to sleep. This means it no longer emits X-rays like active black holes do. According to scientists, our galaxy contains millions of stellar mass black holes. However, finding them is difficult and only a few have been confirmed. When they have a companion star such as Gaia BH1, it is easier to find them. The black hole's energetic interactions with the star make it easier to detect. This occurs when star material spirals in toward the black hole. As the black hole feeds on this material, it emits X-rays, and material jets erupt from its vicinity. For the past 4 years, astronomers have been looking for dormant black holes using a variety of datasets and methods. Previous attempts, as well as those of others, yielded a slew of binary systems masquerading as black holes. But this is the first time the hunt has yielded fruit. Follow-up Gemini observations proved beyond a shadow of a doubt that the binary contains a normal star and at least one dormant black hole. There was no plausible astrophysical scenario that could explain the system's observed orbit that does not involve at least one black hole. And while the discovery was exciting, astronomers still had many questions. According to scientists, the original star that became the black hole would have been 20 times more massive than our Sun. If that's the case, it should have only lived for a few million years. A star has a very short lifespan. However, if that star and its companion star formed simultaneously, the original star should have evolved into a supergiant star. It would then have devoured the companion star in the process. However, the companion star remains, indicating that this did not occur. Could the companion star have made it? It's interesting that standard binary evolution models can't easily accommodate this system. It raises numerous questions about how this binary system came to be, as well as how many of these dormant black holes exist. While this may portend future discoveries of our galaxy's predicted dormant black hole population, the observations also leave a mystery to be solved. Despite its exotic neighbor, why is the companion star in this binary system so ordinary? That is a question we are waiting to be answered. Let's hear what you find the most intriguing about black holes in the comments section below.